Hello everyone, my name is Bhavish Gulabdas and my project partner is Krishnil Ram Sharma. Today we will be presenting on our project which is based on modeling and analysis of resonant wireless power transfer system using fractional calculus. This project was conducted under the guidance of Dr. Utkal Mehta and Mr. Ravneel Prasad.
The outline of the presentation has been listed as follows. The main objectives of this project were to design a wireless power transfer system using the magnetic resonance inductive coupling technique, which was done in semester 1. Then to model the resonant wireless power transfer system using fractional components. Then to compare and validate the new model with the conventional integer order wireless power transfer system. And lastly, to study the effects of varying fractional orders on the performance of the wireless power transfer system. So, just to give a brief intro about the concept of wireless power transmission, WPT was actually invented by Sir Nikola Tesla back in the days as a basis of transferring electrical energy from a source to a load without having to connect wires physically. This has made the lives of people much easier in terms of enhancing safety as well as flexibility. The principle on which it operates is that it uses electromagnetic field of a certain frequency as the medium of transfer. There are many applications in which wireless power transmission is used, such as consumer electronics, for example, mobile phones, laptops, electric vehicles, biomedical implants, as well as some industrial applications such as the use of sensors. Now, moving on to the methodology and design.
Moving on, the diagram over here shows the general schematic of a wireless power transfer system. For the purpose of our project analysis, we have considered the AC source from here right up to the load, which is the resistive load, as will be seen in the following slides. So this circuit over here is basically a series parallel fractional order wireless power transfer system. US over here in the transmitting circuit is a high frequency AC source. R1 is a internal resistance of the transmitting circuit. C1 alpha is the fractional order capacitor of the transmitting circuit, which is also known as the compensation capacitor, while the L1 beta is known as the fractional order inductor. Similarly, on the receiving end, we have a fractional order inductor. We have R2 as the internal resistance of the receiving circuit, C2 alpha as the fractional order compensation capacitor of the receiving circuit, as well as a load resistor.
Hello, my name is Krishnil. I'll be taking on from here. The dynamic model equations of the systems were found by performing mesh analysis. We had three meshes in our circuit, therefore three currents were following, and hence we have three equations as shown in equation 1. We have also considered the impedance of the components on the transmitting side, on the receiving side, and also for the mutual inductance as shown in equation 2. Now, when we incorporate fractionality in the components, the resistance and the reactance now highly depends on the alpha and the beta values. And hence the equation which best supports this are shown in equation 3 for the transmitting side, for the receiving side, as well as for the mutual inductance part. Now, depending on the alpha and beta values, the reactance and the resistive part might increase or decrease. And after performing some computations, we came up with equations for the current which were I1, I2 and I3 as shown in equation 4. Now, when we want to operate our circuit at resonance frequency, that is the frequency of supply equals to the frequency of the circuit, the capacitor values C1 and C2 are calculated using equation 6. And also to remove the negative resistance part from the circuit, signum function is utilized as shown in 7, which removes the negative resistance part and only considers the positive part. This is done because negative resistance causes power to be generated into the circuit. After considering this, the equations for power input, power output and efficiency were derived as shown in equation 9. This table shows the parameters that were utilized to analyze our circuit in the fractional domain, and these parameters were chosen with reference to a textbook.
The first figure of the results show the effect of load resistance on the system efficiency. It can be seen from the graph that as we move from 0 to 2500, there is a gradual increase in the efficiency and it goes to a maximum of approximately 90%. And also according to the graph, it can be noticed that in order to attain a optimum efficiency, say of about 80 to 90%, it is advisable to use the load resistance values ranging from approximately over 500 ohms to say 2500 ohms.
This graph now shows the effect of the load resistance on the output power, whereby since we kept our load resistance at 1000 ohms, we have an output power of 744.5 watts. Increasing the load resistance further would mean that the output power gradually decreases. Both the effects of the load resistance on output power as well as efficiency were seen in the integer domain, whereby the alpha and the beta values were kept at 1.
This graph now shows the efficiency and the output power in the integer domain, whereby alpha 1, alpha 2 and beta is kept at 1. And we can see that a maximum efficiency of 86.36% at an output power of 744.5 watts is achieved. Moving on, both these graphs show how the output power is affected when alpha 2 is changed in the range of 0 to 2, keeping beta at a constant value of 1. And we can notice that from 0.1 to 0.5 the output power decreases, but as we go from 0.6 right up to alpha 2 is equal to 1, the output power starts to increase.
Moreover, when alpha 2 value is from 1 to 1.5, the output power drops from 1.1 to 1.2 and it starts increasing from 1.3 to 1.5. Likewise, in the second graph, the power output drops from 1.6 to 1.2. This figure shows the output power versus alpha 2 when changing alpha 1 from 0 to 2 with beta of 1. Here you can see the output power increases from 0.1 till 1 and it continues to decrease from 1.1 to 2. This plot shows efficiency versus alpha 1 when alpha 2 ranges from 0 to 2 with beta is equal to 1. It was noted that alpha 2 equal to 1.2, maximum efficiency of around 96% was achieved, which is greater than the integer order efficiency value. Here efficiency versus alpha 2 when alpha 1 ranges from 0 to 2 and beta equal to 1 was plotted. It can be seen from the figure that the efficiency increases from 0.1 to 0.9 and it remains constant from 1 to 2. However, a maximum efficiency was achieved at alpha 2 equal to 1.2 and alpha 1 from 1 to 2 with an efficiency of around 97%.
So now this table is a summary of the plots that have been previously obtained, whereby the efficiency and output power at alpha 1 is equal to 1 and alpha 2 is changed from 0 to 2 at beta is equal to 1. And after analyzing the data, it was found that the combinations of alpha 1, alpha 2 and beta at 1.2, 1 and 1 respectively gives a maximum efficiency of 96.23% at an output power of 1282 watts. Moving on, these two plots shows the output power versus beta when alpha 1 is changed from 0 to 2 and alpha 2 is kept at a constant value of 1.2. The reason for choosing 1.2 is because 1.2 gave us the maximum efficiency. As per the first plot, we can see that as alpha 1 is increased from 0.1 to 0.5, the output power increases, as well as from 0.6 onwards up to 1, the output power also increases. Now, as alpha 1 is varied from 1.1 to 1.5, it can be noticed that the output power gradually drops. Likewise, when the alpha 1 is changed from 1.6 to 2, it can be seen that the output power once again decreases. Now, the efficiency plot herein shows that as alpha 1 is increased from 0.1 to 1, the efficiency increases, and from 1 to 2, the efficiency remains at the same value of about 97.22%.
This table summarizes the previous figures and it shows the efficiency and output power when alpha 1 ranges from 0 to 2 with alpha 2 equal to 1.2. After analyzing the data, it was found that at alpha 1 is equal to 1, alpha 2 is equal to 1.2 and beta is equal to 1.02, an efficiency of 97.22% was achieved with an output power of 2015 watt. This slide shows output power versus beta when alpha 2 is from 0 to 2 and alpha 1 is equal to 1. The first figure shows that the power increases from 0.1 to 0.5, and in the second figure the power increases from 0.6 to 0.8 and it starts decreasing from 0.8 to 1. This slide shows when alpha 2 is from 1 to 1.5, the output power increases from 1.2 to 1.5, however it has a spike at 1.1. The second figure shows that the output power decreases from 1.6 to 1.8, however it has a spike as well at 1.9 and then it decreases down at alpha 2 is equal to 2.
So now this table shows a summary of the previous plots and the efficiency and output power versus beta when alpha 2 is ranged from 0 to 2 and alpha 1 is kept at 1. Upon analysis, we can see that the maximum efficiency is obtained for alpha 1 is equal to 1, alpha 2 is equal to 1.2 and beta is equal to 1.03 for an output power of 2665 watts. In order to obtain the maximum output power, we can choose to have our alpha 1 at 1, alpha 2 at 1.1 and beta at 1.02 to achieve a maximum efficiency of 94.34%. Alternatively, if we want to achieve a maximum efficiency, we can choose to have our beta at 1.02, alpha 2 at 1.2 and alpha 1 at 1 in order to achieve a maximum efficiency of 97.22% for an output power of 2015 watts. So finally, upon doing a detailed analysis, we've come to know that these particular values of alpha 1, alpha 2 and beta, we are able to get high efficiency values with its corresponding output power. Also, the corresponding capacitor values are given for the values of alpha 1 and alpha 2.
All in all, it can be said that the objectives of this project were successfully met. Upon doing our in-depth analysis, we were able to see that fractional order components can really improve the overall performance of the system. Results have shown that the system efficiency can be greatly improved from 86.34% to approximately 97%. Results also suggest that this system could be applied in a variety of applications which require medium to high power. The performance of this project can be further validated through experimentation as well.
And these were the list of references that we have used to do our project. Thank you so much for listening. We really hope you liked our presentation. Thank you.